My name is Ronald Kumon, and I'm an assistant professor of applied physics and acoustics at Kettering University in Flint, Michigan. I'll be speaking to you today about characterization of pancreas in vivo using EUS Spectrum Analysis with Electronic-Array Echoendoscopes, which is being published in Gastrointestinal Endoscopy. This study was performed at the University Hospital's Case Medical Center in Cleveland, Ohio. The work was a collaboration with my colleagues in the Division of Gastroenterology at Case University Hospital's Case Medical Center and Case Western Reserve University in Cleveland, Ohio, as well as in the Department of Biomedical Engineering at the University of Michigan in Ann Arbor. In brief, spectrum analysis provides a quantitative and objective method for differentiating between tissue states using backscattered ultrasound signals, and our study has successfully applied this method to the context of endoscopic ultrasound image of a pancreatic disease. To begin, I'd like to provide some background information about spectrum analysis. What is it and why would you use it? The B-mode ultrasound image that you see on the screen of a typical EUS system shows the amplitude of the envelope of the backscattered ultrasound as a function of time, or assuming constant sound speed as a function of space. In this way, simple tissue interfaces, like organ boundaries, will show as well-defined features with straightforward interpretation. However, the complex microstructure of tissue like organ parenchyma or tumors typically exhibit complicated interference patterns arising from closely spaced scatterers, giving rise to an average grayscale value with a superimposed speckle. These regions are harder to interpret and are often characterized more qualitatively by their echogenicity or by their spatial texture. Spectrum analysis is one method for quantitatively analyzing ultrasound signals backscattered from these regions. It is a well-established technique that has been studied for over 30 years in the ultrasound research community. It has also been applied to a variety of clinical contexts, including breast cancer, colon cancer, liver disease, metastases from breast cancer and colon cancer, as well as even tissue changes due to intravascular plaque, among others. Instead of looking at the backscattered ultrasound signals as a function of time or space, spectrum analysis transforms that data so that the backscattered ultrasound signals are a function of their frequency components. Fundamentally, spectrum analysis works because the ultrasound signals backscattered from tissue at different frequencies depend on the effective size and concentration of the scatters in the tissue, as well as local variations in the density and the sound speed. As disease changes the physical properties of the tissue, the amplitude and phase of the frequency components of the ultrasound backscattered from the tissue will also be changed. It's also important to note that this approach makes it relatively straightforward to calibrate an ultrasound system to remove artifacts due to the ultrasound system itself. For example, if you have two different systems imaging the same tissue, you could get two different results simply because the systems themselves are differing. This artifact can be removed using ultrasound spectrum analysis. So why did we feel the need to do this study? While endoscopic ultrasound is generally considered to be a sensitive, non-invasive method for diagnosis and staging of pancreatic malignancy, it remains challenging to distinguish pancreatic cancer from other benign pancreatic diseases. We previously had success in distinguishing between normal pancreas, chronic pancreatitis, and pancreatic cancer, as well as between benign and malignant lymph nodes in two previous studies, both of which have been published in Gastrointestinal Endoscopy. However, these studies were performed using single-element mechanically scanned echoendoscopes. This class of echoendoscopes has largely been replaced by the electronic-array echoendoscopes, which are generally found to have a better image quality, higher frame rates, and other desirable features. Hence, we wanted to perform this study to find out if our previous results would hold or could be improved using the newer electronic-array endoscope systems. The details of our protocol are described in the paper, so I'll only briefly summarize them here. A total of 41 patients were enrolled in the study. 15 of these patients had pancreatic adenocarcinoma as confirmed by histology. 15 patients had chronic pancreatitis as diagnosed by standard EUS protocols, and the remaining patients had sonographically normal pancreas. We acquired our data using the EU-ME1 system from Olympus Corporation. With this system, we used the radial GF-EU160 scope and the curvilinear GF-EU140P echoendoscopes, both operating in the 6 MHz mode. These scopes could operate at higher frequencies, but we kept them at 6 MHz mode for consistency throughout the study. The Olympus system allowed us to simultaneously acquire the B-mode image displayed on the screen, as well as the underlying radio frequency or RF data that is used to construct the image. This represented an improvement over our previous studies in which we had to sequentially acquire the image data and then the RF data by the use of a digitizing oscilloscope. We then, once we had the data, could apply the spectrum analysis method. To perform the spectrum analysis, we first had to acquire calibration. We performed the calibration by imaging specular reflections from the wall of an acrylic plastic cylinder that was filled with a gelatin-based phantom. The phantom was used to prevent saturation of the received signal. We then divided the power spectrum of the tissue by the calibration spectrum. Because the resulting spectrum were quasi-linear, we performed a linear regression to find the slope, intercept, and midband fit, which is the value of the linear regression function at the center of the usable bandwidth. We also computed the root mean square deviation of the spectrum from the linear regression. So what does this study add to our existing knowledge? We found that the midband fit, intercept, and RMS deviation showed significant differences between the cases of pancreatic cancer and chronic pancreatitis. We also found that linear discriminant analysis using midband fit and RMS deviation together for classification resulted in a sensitivity of 80%, specificity of 87%, and accuracy of 83%, with just these two parameters. These results were better than or comparable to our previous studies, reaffirming that the method is applicable to electronic-array echoendoscopes. While the current results were obtained for a particular EUS system, the method can be used for any system where the RF data is available and appropriate calibration can be performed. So what should come next? We would like to perform a study with a larger sample size to further test the method and allow the inclusion of other criteria that have proven useful for computer-aided diagnosis in other studies. We'd also like to perform ex vivo scanning of resected tissue to better understand the microstructural origin of the signals observed with the EUS system. Finally, we'd like to see other researchers take up this method as a means for providing quantitative and more objective method for diagnosis of pancreatic disease. To close, I'd like to thank my colleagues for their work on this project. We'd like to thank Olympus Corporation for their willingness to make the EU-ME1 system and the raw RF data available to us during the study and for providing technical support during the data analysis phase. Dr. Chalk would also like to acknowledge support received from the NIH during the study. Finally, we'd like to direct interested viewers to a companion study from our group using spectrum analysis with electronic-array echoendoscopes to differentiate between benign and malignant lymph nodes, which will be published in 2012 in the journal Endoscopy.